This meeting is being recorded.
Thank you, Hillary, for the introduction. My name is Joe Evinger, and I help coordinate this group's events. This is the Ashby Village Science and Ideas Group. All of our members have all sorts of educational work experience background, but we all share a real interest in science. Currently have well over 50 members now, plus another 50 on our guest list. We meet every month via Zoom on the second Thursday from 3 o'clock until about 4:30. We have different guest speaker each month, speaks to us on a variety of topics, anything related to science and ideas. We rely on our science group members and various committees at Ashby Village to give us ideas about new recruits. Besides our presentation today, I'm actively and always recruiting potential speakers who might speak to us in the coming months. Here's what's coming up in the future. In July, we have a chief scientist with the Ocean Networks of Canada, and the title of his topic is Mining, Conservation, and Bioprospecting Interest Square Off in the Deep Sea. In September, we have a geologist going to talk to us about volcanoes, particularly super eruptions and the possibility of one occurring, or I should say reoccurring, in Yellowstone. In October, we have an anthropologist, a member of our group, who's going to talk to us about ancient human dispersals out of Africa. This is part 3 of his ongoing series of talks. I'm working to get a geologist also to speak to us on mass extinctions of the past, particularly what happened around 60 million years ago. And I have an application in right now to NASA to see if they'll send us someone to speak to us later on this year or even next year. We invite all Ashby Village members to join our group, but anyone interested may join us too. All are welcome, Ashby Village member or not. Today, let's move on. Today, we are very, very fortunate to have Bill Diamond. Bill Diamond is a Silicon Valley technology veteran and currently president and CEO of the SETI Institute in Mountain View, California. Bill has over 30 years experience in laser photonics and optical communications networks, X-ray imaging, and semiconductor processing technologies. Bill holds a BA in physics from Holy Cross and a master's degree in business administration from Georgetown University. He's a current member of the Optical Society of America, the International Astronomical Conference, and I could go on and on. So let me just, the title of Bill's talk today is The Search for Life Beyond Earth, How It Works, How It's Going, and Why It Matters. And with that, I pass it on to you, Bill.
Great. Well, thank you very much, Joe, and I hope everybody can hear me. And before I forget, let me just say, Joe, that most of the work at the Institute is actually funded by NASA. So we have a lot of contacts and good friends at NASA. If we can help you in terms of any particular topic of key interest in bringing in a NASA speaker, we'd be more than happy to do that. So
just for what you offer, Bill.
No, we're happy to help, and you know, the folks at NASA are wonderful, and they're usually, you know, very, very happy as well to share their work.
Thank you.
And I will say before I get started that, you know, one of the things that excited me about this opportunity in particular is, you know, about 100 years ago when I started my career, I remember how fun it was and how interesting it was to often be the youngest guy in the room. You know? And then over the years, that became less and less and less the case. And these days, I'm more often than not the oldest guy in the room. So now maybe I'm among the younger folks in the room again, which is kind of a good feeling. So, but it's a great pleasure to be here with all of you and to see you and happy to tell you about the SETI Institute. So I'm going to give you a talk that'll be about 40-ish minutes. And I have some slides and some animations and pictures. And I will, as Joe said, make a couple of pauses along the way to take questions. But at the end, we'll also do some Q&A. So with that, I'm going to try and share my screen and see if we can get the presentation up and running and loaded. And let's see. So Just make sure you're seeing the right version of my screen. You seeing the full screen there, Joe?
Yes, we are.
Okay, wonderful. All right, so as it says on the screen here, this is a presentation of the SETI Institute prepared for you at Ashby Village, and we'll just jump right in here. So I'm going to start, actually, let me stop this for a moment. I'm going to start with a bit of context. This is a video, and you may recognize the voice on the video, but this gives, I think, kind of a nice summation of the work we do in a kind of a fun way. We call it the trailer for the real life movie we make at the Institute every day. So give a watch and listen.
Finding life beyond Earth is no longer a dream. It's a discovery that will likely be made during our lifetime, and it will change everything. We've been here for more than 36 years at the forefront of a quest that many consider science fiction.
Mars is the closest planet where we might find the possibilities of alien life.
We are home to over 100 explorer scientists.
This is takes your breath away.
Our purpose is singular.
Kind of best to understand what you have in your own backyard as you're looking up into the cosmos.
To understand the origins and prevalence of life in the universe.
What we are doing is to try to understand, are we alone in the solar system?
Why do we pursue our mission? Because the discovery of life beyond Earth will lay the framework for humanity's next steps to the stars.
We are trying to understand why we even exist.
We are the SETI Institute.
All right, so there you go. In case you didn't recognize it, that's the voice of Morgan Freeman. And I consider him to be kind of a tough act to follow, but we'll give it our best shot in any case. So we're going to talk about the search for life and intelligence beyond Earth. And we consider this a journey of ultimate discovery. It's an interesting undertaking, but we believe that also in the process of trying to answer this question, does life exist elsewhere in the universe? It's also very much an introspective line of research because we learn a lot about our own place in the cosmos. We learn about humanity. We learn about our own presence on our planet and the relationship between ourselves and our environment and our planet. So as Jill Towder, one of the founders of the Institute and a pioneering radio astronomer in her own right, likes to say, the SETI endeavor is like holding a mirror up to ourselves. The agenda today, what we're going to cover, we're going to talk about a little history of SETI, provide some context of what this is all about, and also try to give you a sense of scale. How big is this space that we're investigating when we ask questions like, is there life beyond Earth? What does beyond Earth mean? Then we'll meet the Institute itself and tell a little bit about who we are, how we're organized, what we do, and the nature of our work. And then we're going to talk about what we call the roadmap or the guidepost for the field of astrobiology. Astrobiology is the study of life beyond Earth. It used to be called exobiology, but actually a NASA scientist named Lynn Harper, who's actually right next door to us here in Mountain View, California at the Ames Research Center, some years ago coined the expression astrobiology, which is now this endeavor of studying life beyond Earth. We're going to talk about also the methods and approaches we use. So what are the tools and techniques that we use to do the work we do? We'll talk about briefly the education and outreach programs we have at the Institute, because we also like to leverage our science and the fascination that most people have with the kind of work we do to try to promote science literacy and interest in STEM and just science understanding broadly. So we'll talk about that briefly, and then I'll offer some closing thoughts. So that's a bit about the program. And during this, we'll cover the scale and so-called parameter space, or again, the size of our area of investigation. I'll tell you a little bit about the latest technological advancements. So what's new in this field, what new technologies and techniques and approaches are being used in this endeavor. We'll talk about some of the most recent discoveries that have been made in the last couple of decades. We'll talk about also most likely candidates for life beyond Earth, actually nearby candidates for life beyond Earth. And we're going to talk about what we call technosignatures, which are potentially the signatures of life and intelligence that might be detected from a great distance. They could be radio signatures, they could be laser pulses, they could be even atmospheric phenomena that we might look at and say, you know, this looks an awful lot like technology. It's coming from far away. It doesn't look like it's produced by a natural phenomena. And therefore, this could be indicative of life and intelligence beyond Earth. We'll also talk about biosignatures, which are more fundamental signatures of maybe even basic biology and what that means. And we'll talk about the so-called signals of life. So that's what we're going to do. And ultimately, this is about a quest. And we like to think that humanity is on a quest. It's a quest that really began thousands of years ago when our first ancestors gazed up at the sky and wondered, are we alone? And I think it's fair to say we still wanted to know, you know, is our world unique in harboring life among the billions of similar worlds in our own galaxy? And I'll come back to that because we do know that there are billions. Or has life sprung up elsewhere and had the chance to evolve and ultimately lead to the development of complex organisms, perhaps even intelligent creatures, or ultimately advanced technological civilizations? So it isn't really a new question. As I said, you know, it's probably fair to say that some of our earliest ancestors were looking up at the sky with a sense of wonder and curiosity and asking themselves, you know, what is beyond here? What am I seeing up in that sky? And are we alone in our existence here? So if we think about some of the people who've been interested in this, there's Albertus Magnus, who was a 13th century philosopher, scientist, and educator. And he wondered, are there many worlds or but one where life exists? Galileo, of course, was fascinated by this question. Henrietta Swan Leavitt at Harvard in the early 1900s. Winston Churchill was a sort of avid amateur astronomer and wondered himself about the formation of planets and whether planets are a rare or a common phenomena. And it turns out his instincts, which were that they are a common phenomena, were correct. Albert Einstein, we all know, is interested in this topic. The first woman radio astronomer, Ruby Payne Scott. Nancy Grace Roman, who was the first chief scientist and the first real astronomer at NASA, wondered about this. And of course, Carl Sagan, who I'm sure you're all familiar with, Jill Tarter, who co-founded the Institute back in 1984, and who was a pioneering radio astronomer. And for any of you who saw the movie Contact some years ago with Matthew McConaughey and Jodie Foster, the character played by Jodie Foster, Ellie Arroway, was based on Jill Tarter, at least in the first part of the movie. If you saw that movie and remember a young woman astronomer working at the Arecibo Observatory, that big radio telescope in the hills or mountains of Puerto Rico, that's Jill, and that was her work. And there's even a blind radio astronomer in that movie, and he too is based on a real person. So, and then Avi Loeb is at Harvard in the astronomy department. He's been getting a lot of attention lately because of his perspectives on this object called Oumuamua that visited our solar system from interstellar space and then exited again. And he has speculated, based on some analysis he did of this object's trajectory, that maybe this was intelligent technology and not just a visiting rock from some other part of our galaxy. So a lot of people are curious about this. I think it's important to realize that NASA also wants to know. In fact, NASA has 3 questions in science that drive all of its missions, in particular, all of its science missions. The first one is, how does the universe work? The second one is, how did we get here? And the third one is, are we alone? Interestingly, NASA doesn't do much beyond investigating our own solar system to answer that question, because they don't actually fund the more distant investigations using radio telescopes and optical telescopes that we call SETI, or the Search for Extraterrestrial Intelligence. But they do spend a lot of money and resources looking for whether or not there's even basic life in our own solar system. And now with the James Webb Telescope, and we'll come back to how this works, they will also, for the first time, begin to look at planets beyond Earth for the possibility of life, at least nearby planets. So it's fair to say that NASA wants to know, and I think ultimately we all want to know. I think everybody's ultimately curious about this question: are we alone in the universe? What's interesting, however, is that for the first time, we actually have the tools and technology to find out and to answer that question. Technologies and capabilities we've never had before and could hardly have imagined just not too many decades ago. So let's start by talking a little bit about the scale of the problem or the search. How big is this area that we're investigating? So we're going to start this sense of scale or by answering this question with our own solar system. So in our own solar system, there are 8 planets. There are 5 minor planets. There are over 200 moons. There are at least 3,600 known comets and probably more than 1 million asteroids. So it's a seemingly uncrowded space, but it's also a pretty large space. So if you were a photon of light, for example, a little packet of energy leaving the sun's surface, and you were going to travel the 3.67 billion miles it would take to get you to Pluto, it would take you 5.5 hours traveling at the speed of light. So that seems slow. You know, we're used to light being instantaneous. We flick a switch, the light comes on. As far as we can tell, it's an instantaneous process, but it's not. It has a finite speed, the speed of light, and our own solar system is big enough that it takes 5.5 hours traveling at light speed just to get to the edge of our solar system, to Pluto. And if you are launching a rocket, as we did a number of years ago, in 2006 to be precise, and you wanted to travel to Pluto at rocket speed, it would take you 9 years to get there. And that's how long it took the New Horizons Space Telescope, which left Earth in 2006 and arrived at Pluto in 2015. And you may remember that mission because that's the mission that gave us all those stunning and spectacular images of Pluto and taught us a lot about Pluto as a planet that we didn't know before, what it looks like, what it's made of, how cold it is. And it was an extraordinary mission that has continued beyond into the Kuiper Belt and beyond the edges of our solar system. But again, that was a 9-year mission just traveling within our own solar system. And we'll come back to an interesting little factoid about the speed of that rocket in just a moment. But our planet, our solar system, is on the edge of a rather ordinary galaxy. It's a rather ordinary solar system, a collection of planets around a very common so-called M-class star. Nothing particularly unique about it. And if we think about our solar system, it wouldn't even be visible on this scale. So the circle, the little white circle you see, is not meant to represent our solar system. It would be far too small in this picture to be even visible. And to give you a sense of scale, so we talked about the 5.5 hours it would take for light to travel from the sun to the edge of our solar system. Well, our galaxy, the Milky Way, is about 100,000 light years across. That means that same little photon of light would take 100,000 years just to get from one end of our galaxy to the other. And our galaxy has about 300 billion stars in it, give or take. I think it's also kind of fun to point out that our closest neighbor is Alpha Centauri, which is about 4 light years away from Earth. So again, it's very close by in the scale of this galaxy. It's just 4 years, not 100,000 light years. But if we were to go there at rocket speed, and if we go back now and think about that New Horizons spacecraft, which is the fastest object ever built by humankind, traveling in a straight line, it would take that rocket 17,000 years just to get to our closest neighbor. So that's why we talk about, for example, there's not really a good plan B if we mess up our own planet too good. We don't have enough time and resources to get to what might be some nice, friendly planets that might be around Alpha Centauri. So we should think about taking good care of this one, not a place where we can go and ask for a cup of sugar because it's not going to come back anytime soon. So hopefully that gives a little bit of a sense of scale of just our galaxy. And what's interesting and important to realize, it's only one of hundreds of billions of other galaxies. So the picture you see here is called the Hubble Deep Field Image. It was an image taken by the Hubble Space Telescope where they pointed the telescope at the darkest part of sky they could find, where they could see nothing at all. And they left the shutter open for about a month, if I remember correctly. And this is what they observed. And all those smudges, all those little dots and smudgy looking things that you see, they're not stars, they're galaxies. So again, each one of those has hundreds of billions of stars of its own. And so the scale here is really something almost quite unimaginable, but hopefully this helps you appreciate that a little bit. So let's meet the Institute, but before we do that, I'm happy to pause here if anybody has any initial questions.
Bill, could you tell us a little more about this Oumuamua? It wasn't technically a comet. It was just a large rock. Anything else, other details observed about it?
Sure. We don't know what it was. It came and went in a fairly short period. The couple of things we know factually about it. First is that it came from outside of our solar system. So it's not a solar system object, whereas comets and things which periodically come around into our visual arena they are orbiting the sun. They might have very long, very elliptical orbits that might be tens or even hundreds of years, but they are always in our solar system going around our sun. This object, Oumuamua, which by the way was discovered by an observatory in Hawaii, and the name is a Hawaiian word that means messenger. So Oumuamua came from outside of our solar system, and it is in fact the first confirmed object from outside of our solar system that has ever been observed. And that's not to say there haven't been others. There's probably been lots of them, but this was very difficult to observe. And but again, we have more and more advanced tools and instruments looking at the sky all the time. So I have a feeling that we'll see more examples of Oumuamua. But in the kind of instruments that it was being observed with, it was little more than 1 pixel's worth of data. But we could tell a lot by observing that pixel over time, changes in brightness. We could figure out the speed. We could figure out the trajectory. And, it made a loop around the sun, and then it left our solar system once again, and it won't return. What was interesting is the shape of it, from what we could tell by the pixel, and again, the way it reflected light over time as it was observed. It appeared to be thin and flat. Some of the initial images of it, or interpretations of what was observed, suggested it was sort of cigar-shaped. Now, what we have known, again studying the data more closely, it was more kind of pancake-shaped. I mean, it was kind of flat and thin and long. So, of course, that brings to mind images of flying saucers or spacecraft or other things. I think one thing that was odd about the shape is that most objects, for example, within our own solar system, if they're things like asteroids or comets, they tend to be lumpy and bumpy. They might be sort of potato shaped. Certainly as material clumps together and sort of coalesces into larger objects, ultimately gravity and gravitational forces take over, and they ultimately force these objects into perfectly spherical shapes, which is why stars and planets are generally perfect spheres. But smaller objects can be kind of bumpy and lumpy, but long, thin objects aren't too common. So that was one thing that was odd about it. The other thing that Avi Loeb observed in his analysis was he felt that the speed of the object, and particularly the speed with which it went around the sun and then accelerated back out of our atmosphere, didn't seem to follow the normal Kepler laws of orbital velocities. And so for him, this suggested, well, I don't know, this math looks a little funny, seems to be going awfully fast. And maybe this is alien technology. I think Avi's kind of gone a little bit out on a limb in not only suggesting the possibility, but perhaps almost coming to the conclusion that this was. And so it's become quite a controversial topic. But of course, he's a respected astronomer. People take him seriously, but many of his colleagues say, Avi, you've maybe gone too far here. But that's what we know about Oumuamua. It's certainly a fascinating object. And again, I'm sure we'll have the opportunity in the years to come to observe others like it.
Thank you. Any other questions?
All right, well, I'll continue on and we'll have other additional opportunities for questions. So want to have you meet the Institute. So at the SETI Institute, our mission is to lead humanity's quest to understand the origins and prevalence of life and intelligence in the universe and share our work with the world. Couple of key words in here. One is life and intelligence. So again, NASA is very interested in understanding the origins and prevalence of life in the universe, not necessarily, however, intelligence. They're not looking for technology as a proxy for life and intelligence. They are, of course, looking for life. The Perseverance rover on Mars, that's its sole mission and its sole purpose. So they're interested in the same question, but they sort of stop short of the intelligence and technological part of that search. The other key area here is sharing our work. We feel that that's not only something that's very important for us to do, but it's a responsibility that we have, because much of our work, not all of it, is funded by government grants, most of which are from NASA, some from the National Science Foundation, the US Geological Society, and other government agencies. But that means that the taxpayer ultimately and indirectly is responsible for the work we do, and therefore everybody has the right to know what we're doing. And so sharing our work is an integral part of our DNA, if you will. And that's why we have both education programs and outreach programs where we can talk about the work we do and share it with everybody. So these are kind of differentiating parts of our mission statement. We're organized around 3 centers of activity. So we have our Center for Research. It's called the Carl Sagan Center for Research. That's our research center whose job is to do exploration. We have our education division to inspire and teach. And we have our outreach division, which is to engage the public and again, promote science literacy and share the work that we do. Our team, the SETI Institute, is home to more than 100 PhD scientists. We have 34 education, communication, and professional administrative staff. We are a 501c3 nonprofit research institute. So a lot of our work, as mentioned, is funded by federal research grants and contract, but a lot of our work is also funded by private foundations, private individuals, corporate partners and sponsors, and others who care about our work. We are a top 100 NASA contractor, and we collaborate with academic and research institute partners all over the world. And fundamentally, we like to think of ourselves as scientist explorers, and we're following a principle that is also very important to us, and that is that the nature of our work is such that if we were to make the extraordinary claim of we have discovered life beyond Earth, or we have discovered technological or intelligent life beyond Earth, that extraordinary claim would require extraordinary evidence. And Carl Sagan famously said this: extraordinary claims require extraordinary evidence, and that is built on similar perspectives offered by the French mathematician Laplace. So we do rigorous science at the Institute, and we would obviously back up any major discovery with confirmations and observations from other scientists and other research institutions and organizations around the world before we go out on a limb and say we have a discovery. But given the magnitude of the question and the sheer scale of the cosmos and the parameter space that we're looking at, a fair question to ask is, where do we even begin? How do you even think about this? So we're going to talk now about the roadmap, if you will, or the guideposts that we use to sort of direct our efforts. So I'm going to start with the following, and that is, what if somebody asked you to calculate, just to estimate the number of technological civilizations that might be in our own galaxy. And what if that someone or that organization happened to be the National Academies of Science? Well, that is precisely what happened back in 1961, where the National Academy of Sciences went to Cornell astronomer, Dr. Frank Drake, and asked him to gather some of his colleagues together and talk about this question of whether or not there is scientific merit for looking for the signs of technology as a proxy for life intelligence and intelligence beyond Earth, using instruments like radio telescopes and others to do so-called SETI. They wanted to know if the scientific community thought this was a valid endeavor. So Frank gathered a group of scientists, about a dozen, including Carl Sagan and astronomer Otto Struve and others. They met at the then relatively new National Radio Astronomy Observatory in Greenbank, West Virginia. And they met to ponder this question. So Frank's had the job of sort of establishing the agenda for that meeting. And he felt, well, if we're going to try to answer this question, how many technological civilizations are out there, which is really at the heart of whether or not this is a worthwhile endeavor, we want to know a few things. We'd like to know, what is the birth rate and life cycle of stars? We'd like to know how many stars have planets. We'd like to know how many planets are habitable or Earth-like planets. You know, they're at the right distance from their host star, where the energy flux coming from that star is sufficient to maintain sort of liquid water temperatures. We'd also like to know that if there are habitable Earth-like planets, how many of those or what fraction of those would go on to develop life? And if life happens, in how many instances would evolutionary processes allow life to develop complex organisms and ultimately an intelligence? And if that happens, how many of those worlds would go on to enable the rise of technological civilizations? Technological civilizations being the kind that we might be able to observe or detect from great distances, because their technology would be observable from great distances. And lastly, he felt it'd be important to figure out how long a technological civilization might remain detectable. And they might no longer remain detectable, either because they go extinct, or perhaps they evolve into some other species which perhaps no longer needs technology or uses technology that we have the ability to detect or observe or even imagine, or perhaps they get back into a more symbiotic relationship with their planet and its resources, and therefore they go dark. So these were the questions that Frank thought were worth addressing in this initial meeting. And then he realized, in looking at these questions, they could sort of be assembled into a kind of a formula. So he came up with what is called the Drake equation, where the number of technological civilizations is a function of the birth rate of stars and how many stars have planets, how many of those are habitable worlds, how many habitable worlds go on to develop life and intelligence and technology, and then how long do they last? So that has become known as the Drake equation. It's considered by some to be the second most famous equation in science, the first, of course, being Einstein's E = mc squared. But if you're interested in it and you Google Drake equation, you'll see a lot of information about it. Frank is actually was the first chairman of the board of the SETI Institute after its founding in the early 1980s. He's actually still with us. He's a gentleman now in his 90s, lives down on the coast. Marvelous, amazing, and inspiring gentleman, and again the father, if you will, of the Drake equation. So the Drake equation has become again somewhat of a roadmap for astrobiology, because it sort of lays the groundwork of the things we want to look for or study if we're answering this question about, are we alone in the universe? So with that, I want to pause and have you look at this picture and ask you what you see. And maybe somebody can just turn on their mic and say, you know, what do you see in this picture?
Somebody want to make a guess?
Milky Way.
The Milky Way? And what else are you seeing in this picture?
I see a human being.
There is a human being in the picture. There's a body of water. But if we're looking up in the sky, we see the Milky Way, we see stars, all kinds of beautiful objects. there's something else that you see that you don't realize that you're seeing when you look at this picture, or if you go out on a starry night and look up into the sky, and that is you're not looking just at stars, you're looking at solar systems. You're looking at planets that statistically, every single dot in that sky, every single white smudge in that picture is a star with planets around it. And that's not science fiction, it's science fact. It's relatively new information, but it's kind of stunning and pretty spectacular. So think about that. And the next time you're out on a starry night, and particularly if you're with somebody who hasn't yet been clued in on this, you can point up to the sky and say, you see that up there? That's not just a star, that's a solar system. So how do we know that? So we know that based on a mission from NASA called the Kepler mission. And this was, in my opinion, this is perhaps the most profound science mission in the history of humanity, certainly in NASA's history, because it profoundly changed our perspective of our place in the cosmos, and it answered perhaps one of the most fundamental questions of whether or not planets were this rare thing or something quite common. So what did Kepler do and how did it work? Kepler was following up on some early discoveries using other methods of big planets around stars. And scientists had begun to observe in the mid-90s that they could look at some stars in the sky and they would see those stars kind of wobbling a bit and not being perfectly still. And they at first, after observing this, it was a couple of years before it was realized what this phenomena was a result of. But it turned out that phenomena was a result of large, like Jupiter size, the big gas giants that are in our own solar system, big planets orbiting around the star. That means that the center of gravity of that system is no longer the middle of the star, but it's somewhere outside. And so the whole thing wobbles a bit. And so that was called the radial velocity method. So a number of planets were observed, and it gave rise to the question, well, gee, so does that mean planets are common, or is this a rare thing? And are they all big, or are there other ones? So the Kepler mission, which was actually a mission that was born right here in Mountain View at the NASA Ames Research Center, the principal investigator or chief scientist, the guy behind the idea, was a gentleman named Bill Barucki. And the Kepler mission sought to answer that question. He felt that we could build a telescope that could stare at stars for a long period of time. And if a particular star happened to have a planet going around it, and that if it just happened that the orientation of the orbit of that planet was in our line of sight, we might see that planet transit in front of the star, as you see in this animation. And if we're measuring very carefully, we might be able to measure the amount of dimming of that starlight that is caused by that so-called transit of that planet. And so that was what Kepler did. Now, it was not able to see stars in this big, bright, bold manner that you see in this animation. It was looking at about 200,000 stars at the same time. It was staring at them in a fixed field for about 3 years. And so even in that telescope, the stars appeared as tiny little dots. But by carefully monitoring them, it was able to look for these transits. And if they happened periodically, and we could follow up with careful observations, even with other instruments, we could confirm that this phenomena of this periodic dimming of light was because of a planet. And but it's also fair to say that this was a very, very sensitive instrument, so sensitive that NASA at first didn't even believe it was possible. And it took Bill Barucki 5 efforts to convince NASA that this technology was doable and that this could be done. But to give you a sense, if you thought about an Earth-like planet orbiting a sun-like star, and somebody was observing us from far, far away, so that the sun was just a little point of light, an Earth-like planet going around that, our sun, would dim the sunlight by only 1 part in 10,000. So a tiny, tiny amount. But the instrument was capable of observing that slight distance. So this animation and the dip you see there is a huge exaggeration of how the data actually looked, but it gives you an idea of what the technique was. So what did Kepler discover? Well, before Kepler, as I mentioned, a lot of other planets had actually been observed, and all of this didn't even start until the 1990s. But we found lots of Jupiter-sized planets and Saturn-sized planets, big planets. And so the size of the planet is going up as you go up into this diagram. So Earth-sized planets would be down towards the bottom, Jupiter and Saturn-sized planets up near the top. And you could see that, the earliest discoveries were these great big planets. Now, you might conclude that, well, it must be that if there are other planets out there, mostly these great big planets that probably wouldn't be very hospitable to life. But, you might also conclude that, well, those were the easiest to find, so maybe that's why we found them. So let's send up this Kepler Space Telescope and see what we can find. That's what we found. So the Kepler Space Telescope, in looking at its field of view, found thousands of planetary systems. And most, if you'll notice the graph, were sort of Earth size, or kind of between Mars, Earth, and Neptune in size. So a huge population. And we also know that, statistically speaking, the probability of this orbit being in our line of sight versus being in any other kind of formation was less than 1%. So based on the number of planets that were observed and confirmed, and then doing the math backwards because of the low probability of this orbital alignment, the conclusion was that planets are everywhere. They are ubiquitous. They are, in fact, most likely a natural byproduct of the formation of stars themselves. So, the planets in our own solar system were formed after the birth of our own sun. And the reason the planets are on the same plane is because it's about the sun spinning up material and then ejecting some material all on a plane, like on a plate or a dish, and then that material coalescing together into lumpy clumps that ultimately became the planets. So this is a profound discovery, because now we know planets are everywhere. And that's why I said in the previous image, when you look up at that starry sky, you're seeing planets and solar systems and not just stars. So what did we learn from Kepler? The Kepler mission taught us that basically every star in the sky has one or more planets. It taught us that the majority of planets fall between Mars and Neptune in size, kind of like Earth. It also taught us, because we could figure out the distance of the planet from its star, and we could tell by the brightness of the star its energy flux. So we could figure out and we could tell the size of the planet. So we could figure out which planets were sort of rocky and Earth-like, and what percentage of them were the right distance from their star that they could potentially be habitable. In other words, the temperature could, in principle, depending on the atmosphere, be just right for liquid water. Well, that number turned out to be 20%. About 20% of all these observed planets are rocky, Earth-like planets in the habitable zone of their star. So the implications of that are pretty amazing, because they imply that potentially 10 to 60 billion, with a B, Earth-like habitable zone planets are in the Milky Way galaxy alone, never mind the hundreds of billions of other galaxies out there. So that's why I say this is a pretty profound mission, a pretty amazing discovery. And of course, from my point of view, it makes the work we do at the Institute all that more sort of interesting and compelling. So looking back at the Drake equation, how much do we know now? So what we knew back in 1960, when Frank Drake was first gathering with his colleagues, we knew at that time something about the birth rate of stars. We didn't know anything else about any of the other variables to the right. We didn't know the fraction of planets stars that had planets, or how many were in the habitable zone, or how many would go on to develop life. We didn't know any of that. But thanks to the discovery of planets and ultimately the Kepler mission, now we know what fraction of stars have planets, basically 100%. We also know what fraction are habitable Earth-like planets in their planetary system, and that's about 20%. We still have a lot that we don't know. We don't know what fraction, if any, go on to develop life or intelligence or technology, and therefore, the duration of that is still a question as well. So there's a lot that we don't know. I call that job security, which is not a bad thing. But anyway, again, this unknown means that there's plenty of more work to be done. But also, paradoxically, it's like the age-old thing in science in general, and that is that the more we learn, the more new questions come up. So next I want to talk about methods and approaches, but again, I can pause here for a second, Joe, if anybody has any questions before we move on.
Okay. Well, I would like to ask, is Mars considered to be in the habitable zone by this definition?
Yes. In fact, there are 3 habitable zone planets in our solar system.
Venus.
Venus, Earth, and Mars. Venus is a good example of what can go kerflooey if you have, runaway greenhouse gases, because that's what Venus has in its atmosphere. It has massive amounts of greenhouse gases, so the temperatures are extraordinarily hot and unsuitable for life to exist on the surface of Venus. However, there's a recent mission that discovered an interesting molecule called phosphine in the atmosphere of Venus. Phosphine, as far as we know, is a molecule that is only formed by biological processes. So it gives rise to the question of whether there's biology, perhaps, in the upper atmospheres of Venus, where in fact there are layers of the Venetian atmosphere that are at sort of room temperature. So it's an interesting question. There's questions as to whether or not the phosphine discovery was real. So that's not 100% confirmed yet. And of course, there's another question is, well, maybe there are other non-biological processes that can produce phosphine. But anyway, it's an intriguing discovery. And Mars is also in the habitable zone. And Mars, we also know at one point in its past, in its early life, Mars was a planet with an atmosphere, with oceans, and it looked kind of blue, looked a lot like Earth. Still, there's a lot of water on Mars, but Mars is smaller than Earth. It cooled faster than Earth. The core, most planets, the core material is iron. And when molten iron circulates, it's a little bit like an electric motor. So when you spin iron, it creates a magnetic field. So the Earth has a magnetic field. The magnetic field shields the planet from lethal radiation that would be, dangerous or lethal to life on the surface. So when Mars had its gravity, its core cooled and its magnetic field then disappeared, then the solar wind, the radiation and particles that are emitted from the sun ultimately stripped away its atmosphere. And so Mars only has an atmosphere that's about 1/100th of the Earth's atmosphere in terms of its density. But there's still water on Mars. A lot of it is locked up in the poles. There's liquid water that runs, and there's certainly the prospect and possibility that there's life below the surface of Mars, away from the dangerous radiation. There could be microbial life or even more complex organisms. So it's an intriguing planet. And we also know it was warm and wet because we know that there are minerals on the surface of Mars, so-called clays. And clay as a mineral composition is only formed in warm, wet environments. So we know a lot about the past of Mars. And that's why it's so intriguing to look for life there, either signs of life still present or signs of extinct life from past epochs. But yes, so here in our own solar system, we have 3 planets in the habitable zone. I'll talk more in a little bit about other places in our solar system that could also have life that aren't in the habitable zone. So it makes that equation even bigger. A couple of more hands.
Yeah, I see a couple more. Yeah, go ahead, Sarah.
Oh, maybe I'm jumping ahead, but how does SETI define intelligence?
That's a great question. I'll tell you, the first question is, how do we define life? And
okay.
And the answer is not very well. So the scientific community, if you read up on this, you'll realize that there is no good working definition for life in the sciences. There's lots of different ideas and thoughts about it. There's lots of information and knowledge about what life does. There's not a lot of information or knowledge about what life is. There are lots of different thoughts and ideas about it. But we're actually going to be hosting a workshop later this year that is trying to investigate questions around the origins of life, the nature of life, and how we define it, and also based on how life manifests itself, what different ways there might be to look for it. Intelligence is something else again, and so there isn't really a good sort of single answer for what is the definition of intelligence, but certainly, there are different things that intelligent objects or organisms have in common. One is that actions, which could be as simple as, mobility and motion, seem purposeful and with intent and purpose. Others would include the ability to communicate and to share information within a species. And so those are certainly, some signs of intelligence. And then you can watch and observe behaviors. So we know, just for example, in observing octopuses, that they are perhaps much smarter than we might have first thought. They are incredibly intelligent creatures, as are whales and dolphins. But even look at bees, and bees can be extremely intelligent. They communicate with each other. They don't use sounds or light, but they use the physical motion of their body, the so-called bee dance, to communicate. Plants communicate through chemical secretions, animals through different kinds of vocalizations. And we have actually a scientist who's currently studying the vocalizations of the humpback whale, because he's applying a mathematical tool called information theory that was designed to study telecommunications and human speech. He's applying that to vocalizations of the humpback whale, because he's trying to understand whether or not information, regardless of how it's transmitted, whether it's sound or light or chemicals or what have you, whether information has certain patterns in its transmission that we can pick out. In other words, is there an underlying mathematical construct to the transmission of information that would allow us to say, if we pick up some phenomena that has some sort of modulation or something changing in it that we can observe, if we could tell if there's any patterns there that would suggest that it's information. Because it would be really a sad thing for us to observe some interesting phenomena that could be information, but not to recognize it as such. So that's it's a fascinating topic in its own right, for sure.
Thank you. I think
Sure.
we'd learn from hearing more about that.
Yeah, there's, so actually, we talked about, life and its definition. We're having a workshop this fall about it. In the spring, we're going to be having a workshop on intelligence, in fact. And Lawrence Doyle, who's our scientist studying the humpback whale, and it's an interesting collaboration between an astronomer and astrophysicist, that's Lawrence, and a marine biologist at the Alaska Whale Foundation. So this is truly interdisciplinary, multidisciplinary science. It's fascinating work they're doing, but we're going to bring together, scientists and researchers from all different walks of life in the natural sciences and have that conversation. And then next fall, we're going to follow that up with a third conference, which is going to be about, how to reimagine looking for signs of technology. Could aliens use gravitational waves or neutrinos or even DNA as a means of communicating, or as a means of are these things that we could look for? So they're all great questions.
Thank you.
Susan.
I'm going back to the sort of astonishing slide that showed all the Earth-sized and possible habitable places, and the fact that the data seem to kind of skew to the left, and if that conveyed information about where they are they closer or further?
Sure. Let me go back.
It could
That picture. So when you talk about skewing to the left, what's on the left side of this chart with all the yellow dots? So the x-axis is the orbital period in days. What's interesting is that this data found a lot of planets with very short orbital periods, like planets that go around their sun in 100 days, or even 10 days, or even a day, or even less, which is extraordinary. The other thing that was extraordinary is, the fact that there are Jupiter-sized planets zipping around their host star extremely fast. I mean, I think scientists were and are still sort of baffled by this discovery. We're not yet clear or sure what the implications of these short orbital periods are, and whether that gives us any other indication of where to look. But it's certainly fair to say that if we could look at in any direction at this point and observe stars or planetary systems, which would have a multitude of different sized planets with different orbital periods. But it does look like the majority of planets, at least in the Kepler data, have orbital periods sort of between 10 and 100 days, Earth days, and are a little bit larger than Earth. That's sort of the center of that distribution. A follow-on mission from NASA called TESS, or the Transiting Exoplanet Survey Satellite, is mapping the entire sky. So unlike Kepler, which just stared at one bit of sky for 3 years, this is staring at bits of sky for 30 days at a time. And again, you can see from this graph that there are a lot of planets within these short, less than 30-day orbital periods. But it's mapping the entire sky to find additional exoplanets that are most likely, in most cases, are going to be closer to Earth. So we'll know a lot more about the distribution of planets, their orbital period and size, as the TESS mission continues over the next several years.
Wow. Well, a short orbit would at least make it easier to get grandkids to take a nap.
One would think, or one would hope. All right. So let me continue.
I think we have one more hand up.
Okay.
Joan. Have to turn
Yes.
this.
Here's my question. You have been assuming, and maybe it makes sense, that all of these planets and all of these systems are like our solar system. That is, they're organized as a star surrounded by planets in orbit. Is that an assumption or a discovery?
That's a discovery. So we've been able to identify, and observe, in many cases, more than one planet orbiting the star. Now, there are many others for which we only have one data point. In other words, we have observed one planet. That doesn't mean that there aren't more there, but we may not have discovered them yet. This is why we say, statistically speaking, every star in the sky has one or more planets. But I'm kind of extending that a little bit when I say that these are solar systems, because my own assumption is that it's almost certainly going to be true that there are more than one planetary type body surrounding stars, because again, what we now understand about how planets are formed sort of implies that there's going to be some number of them. An interesting planetary system has been discovered called the TRAPPIST system, and it's so called because it was a Belgian telescope that discovered this system. Has 8 planets around it, and this is a system around a smaller class of star called an M dwarf star. These are older and cooler stars than our own sun. They have longer lifespans, and they also happen to be the most abundant kind of star, at least in our galaxy. And so this is a system with 8 planets, and again, 3 of them are in the habitable zone of that planet. So it stands to reason, I think, that most of these systems are going to turn out to be solar systems, meaning there'll be multiple bodies in orbit around the star, the host star. Now, some of them could be, just planetesimals, i.e. small bodies, but I think, many will be larger bodies that we would consider and define as planets.
Well, my question was really about the notion of a system. And so there are no systems where the star or the sun rotates around, revolves around the planet, or planets that do figure eights, or any other kind of system, but elliptical orbits.
Sure. Yeah. So as far as we know, again, the systems we've observed have been, circular or elliptical, but usually not too eccentric orbits. And again, the logical reason for that is that they are born as a result of this, the spinning mass of the star itself. So the distribution is going to be, somewhat random, but it's likely to have circular orbits ultimately when they reach a stable period. But what's really interesting is that there are so-called binary star systems, and Alpha Centauri is a binary star system. In other words, there's two stars in orbit around each other. And we know that at least in one case, that there is a planet around Alpha Centauri b. And so, we've discovered one planet in that system. Now that planet is going to have a fairly complex orbit because it's going to get tugged by the other star as well. And we're not 100% sure. We have observed another star in the Alpha Centauri system. So it could be a three-body system or a tertiary star system. And if any of you have ever heard of or read the now famous Chinese science fiction trilogy called The Three-Body Problem, or the first book is called The Three-Body Problem, it's about Alpha Centauri and about a three-body system of stars, which makes life very complicated for the intelligent species that evolved on one of the planets of that system. So it's a great question, because indeed there are complex dynamics for systems where there's more than one star influencing a particular planet. That's for sure. All right, let's see. I'll continue on here. In terms of methods and approaches, so we like to think that we have a kind of a structured approach to answer this basic single science question, which is, are we alone in the universe? And we investigate that through three domains of activity. The first is the structure of the universe. The second is planets and habitability. And the third is life, complexity, and intelligence. So these are all the different areas that scientists here study. And the scientists are organized around 6 specific disciplines. So they include astronomy and astrophysics, exoplanets, which is the study of planets beyond Earth. And in fact, the SETI Institute had a big role in the Kepler mission. We actually managed the data pipeline for NASA for that mission. And our scientists wrote the so-called algorithms that did the detection of planets, that measured those little blips to determine whether an observed phenomena was a planet or some other bit of information. So we had 18 data scientists on the Kepler mission, and I'm immensely proud of the role the Institute played in that mission. So we have an exoplanet team. We have a team that is focused on planetary exploration, which is mostly involved in studying our own solar system. We have a group that is called Astrobiology. That particular group in this instance is mostly doing extremophiles research, meaning they're studying life in extreme environments on our planet, which right now is the only laboratory we have for life. But they're trying to understand, how big is that envelope of conditions under which life can exist? And we have learned over, the recent years and decades that the envelope of conditions under which life can exist is much bigger than we thought, that life has an extraordinary ability to exist in even environments that, again, just a couple of decades ago, we would have thought is impossible. We study climate and geoscience. Geology and climate obviously influence biology, and the reverse is also true. So we talk about the so-called co-evolution of life and environment and how these two interact and inform one another and impact one another. And then lastly, we have radio and optical SETI, using optical telescopes and radio telescopes to look for signs of technology beyond Earth. So those are our research disciplines. And basically what we do is we do NASA science mission support. So we've had support for almost every mission that NASA has launched, and including Viking, which was before the Institute was formed, but Frank Drake was principally involved in that. So we've been involved in NASA science missions from our very outset. We do a lot of field expeditions. A lot of that is to, again, study life in extreme environments, and also to understand what are the tools and technologies that we might need to look for other life on other worlds, like Mars, for example. We do laboratory research, chemistry, physics, biology, geology, etc. We use ground-based observatories, radio telescopes and optical telescopes, and also space-based observatories. Our scientists use the Hubble Space Telescope. Again, we were a big part of Kepler, now TESS, and also the James Webb Space Telescope, or JWST mission, which is brand new and and we're very excited about that. And then lastly, we do technology and instrumentation development. So actual hardware, including telescopes and signal processing, computers, et cetera. But for example, on the Curiosity rover, which has been on Mars now for several years, there's an instrument called the ChemMin, for chemicals and minerals instrument. It's a so-called X-ray diffraction instrument, and surface samples of the Martian surface are poured into this instrument, and we pass X-rays through the samples of material. And with that, we can determine what the material is made of. We can determine what are the elements that are composing the surface of Mars in different locations. So that's a SETI Institute instrument on board Curiosity. And ultimately, we're just trying to understand the structure of the universe. We're trying to learn about planetary environments and habitability and the nature and origins of life, and of course, ultimately the evolution of intelligence and technology. So a typical day at the office includes support for NASA missions like Cassini or TESS or Curiosity or New Horizons, the Pluto mission, and more. And of course, now we're part of the Curiosity, or rather the Perseverance rover mission on Mars. And then we're again using ground-based radio telescopes and optical telescopes like the Very Large Array in New Mexico. The picture with the tents is from the Atacama Desert in Chile and the high Andes in Altiplano. The next picture is our research team in Antarctica at Lake Untersee, where they dive below 12 meters of ice in these permanently frozen lakes and find thriving colonies of cyanobacteria, some of the earliest life forms from our planet. So they again learn a lot about the origins of and evolution of life, but also life in extreme environments. And the picture on the right is a project called Lakelander, which was about developing floating research laboratories, if you will, that might be used on future missions to places like Titan, a moon of Jupiter that is quite interesting and has some interesting prospects for possible life as well. So these are just some examples of what we do in terms of exploring terrestrial analogs. In other words, we go to places like the Andes and we go to the tops of volcanoes that have environmental conditions that we would claim are analogous to certain places on Mars. So it helps us, again, understand what tools and techniques we might use and need on Mars to look for life. Or we're characterizing the fingerprints of life. So there's Dale Anderson about to dive below the surface of Lake Untersee in the Antarctic to study the bacterial colonies there. And then instrumentation development and exploration strategies. And this is, I'm going to introduce you.
Good morning and welcome to the members and guests of the Explorers.
I'm going to let Natalie Cabral talk to you for a minute. Natalie is the director of the Carl Sagan Center for Research. So she's the head of research here at the Institute. This is a video that was done in the field just a couple of years ago when she was in the Atacama Desert with her team, and we were meeting with the Explorers Club in New York. And so she just gave a little short explanation of what goes on in her work. Go back to that.
Good morning and welcome to the members and guests of the Explorers Club. My name is Natalie Cabral. I am the director of the Carl Sagan Center at the SETI Institute, and I'm an astrobiologist and a planetary scientist. This is a beautiful morning in Salar de Padranes in Chile. We are in the Chilean Altiplano, and what you see behind me is our base camp. Has been our base camp for a few days now. This is literally a little city behind me. We have about 15 tents, 2 domes. It's an absolutely fantastic landscape. It's otherworldly. We have the feeling that we are actually walking on a different planet, and we have been for several days now. We have a project which is funded by the NASA Astrobiology Institute, which is actually studying ways of detecting biosignatures. It's in support of future missions to Mars. But I mean, in general, it's going to be helping the development of new techniques, new instruments, and new methods of detection for the search for life in the solar system. Salar de Padranes is the first site on our trip. We will stay in the Altiplano between October 27th, which is when the team arrived here, until November 19th. We will be visiting the El Tatio geysers, which are at about 4,300 meters. Here we are at about 3,500 meters at Paranales. And then we'll go even higher. We'll go to Laguna Lejía and Laguna Aguas Calientes, all in the San Pedro, the Atacama region. And we will end our trip by climbing the Simba volcano that is close to 20,000 feet. For each of the sites, the goal is the same. We're here to collect a lot of data to understand how we integrate these data from orbit to the ground, to the lab, to develop new detection methods, exploration strategies, and instruments. And with that data also, we are going to be able to train new systems supported by AI and machine learning, which will help us ultimately develop the new exploration strategies, the new generation of exploration strategies for the search for life in the solar system. This project is part of the Astrobiology Research Division of the SETI Institute, is connected to the mission of the SETI Institute in that it provides us with answer, or at least ways to find answers to, are we alone in the solar system? Basically, what we are doing is to try to understand how to detect life that is not visible or traces of past life that it might be hiding somewhere. I would like to end by first thanking you for having me with you, at least for a short moment. And I am so very pleased that I was able to share with you the landscape we have behind us. It's, as I said, when we started, absolutely stunning. And also, I would like to show you the SETI flags that we are deploying. Here is flag number 1. I am always taking it with me. That's second or third time now that it is deployed in the Andes. Flag number 2 is actually a few thousand kilometers south of here with Dale Anderson in Antarctica. And flag number 3 flew about a week before we left on the Sophia airplane with teachers and Pamela Harmon and Bill Diamond. So thank you very much for having us with you. And on behalf of my team, I wanted to say thank you and goodbye from Salar de Paranales and the Chilean Altiplano. Good night.
All right, so that's gives you a little idea of what happens in the field and the kind of work that is done studying the astrobiology projects in the field in places like the Atacama Desert and the Altiplano. So that's the picture of the volcano. And so the team climbed that volcano with gear, including scuba gear, because among other things, they dive into the water. So you may barely be able to make out in the bottom left picture. I'll try to circle it here. There's people and a tent set up. So that's at the top of a volcanic crater. But they dive in that lake at 20,000 feet. And just as Dale Anderson finds life forms below the ice in Antarctica, they find life forms in an otherwise lifeless environment. And again, this helps teach us about tools and techniques and about life itself in terms of understanding its prevalence elsewhere in the universe. And these are just other images of that work. This is an example. That's a picture of a cyanobacterial mound or ecosystem underneath the ice in Antarctica. So again, that's a thriving colony of microbes, microbial life. That's Dale emerging from the ice there, and a picture of the environment that he's working in. So all of this is, again, trying to understand and imagine the future of planetary space exploration. It includes designing and developing rovers and floating laboratories, even spacesuit design, habitat design. All of these things end up being the sorts of things that our scientists and researchers and engineers get involved in. And we're also involved in using the technology we've developed for planetary exploration to monitor changes in our own planet. So as we go to these remote parts of the Earth and we study them and we study life and habitats and environments, we also see the impacts of climate change. And therefore, our research informs these studies as well. And we're increasingly working with groups like the Earth Science Division within NASA to help understand what's going on our own planet and what are some of the mitigation strategies that we might have to deal with the problem of human-induced climate change and environmental impact. This is just kind of a fun chart to give you an idea of where our work takes us. So it basically takes us all over the planet, from the two poles to India, Australia, China, Africa, Europe, and so on. So again, the field work is quite extensive in terms of its coverage of our planet. One of the things that I think is important to convey here is what we try to do as well is be a little different than the typical research that is organized in academic institutions, where things are siloed into different domains like chemistry or physics or astronomy or biology, et cetera. I mean, it's understandable that humans sort of break down the natural world into pieces that we can understand, but ultimately what's really interesting is looking at the interconnection between all these domains and disciplines. And that's what we think about as the multidisciplinary science of the Institute, why we love to put together chemists and physicists and astronomers and marine biologists and others, because I think we realize that sometimes the most interesting insights and the deepest insights happen at the intersection of domains and not necessarily within the domains themselves. So basically, there's three methods to search for life in the universe. There's in situ instruments, meaning send your technology to the place of interest and see what you can find. There's remote sensing. We use big telescopes to do things like look at planetary atmospheres of planets beyond our solar system. And the James Webb Space Telescope will be able to do that and see if there are markers or signatures of biology in those environments that might suggest the presence of life. And then ultimately we can use radio telescopes and optical telescopes. This is our own radio telescope array in Northern California called the Allen Telescope Array. We can use these technologies to look at phenomena at great distances, even across the other side of our galaxy and potentially even outside of our galaxy, to look for phenomena that we would say is not produced by nature and might be indicative of an intelligent or technological species elsewhere. So in terms of biosignatures, technosignatures, and signals, there are, again, ways to look at planetary atmospheres and break them down into their component parts and see if they have hints or suggestions of the possibility of life inside. There are even other things that we call technosignatures, where some, such as Freeman Dyson, have imagined that truly advanced societies might build enormous structures around their own stars to harness their star's energy and use it for their own purposes, so-called Dyson spheres. And these would also be phenomena that could potentially be detectable with the right kinds of instruments. So there's lots of different ways to look for life, both near and far, that are deployed in the work we do. And so again, for the solar system, this is about the limit of where we can do in situ investigations. In other words, this is where we can actually send hardware. We can send spacecraft and instruments. And right now, at least at the level of human technology, we can't really send instruments further afield than that. But there's plenty of interesting candidates here, not least Mars and Venus, but also some of the moons like Enceladus and Europa, which are frozen moons with liquid oceans underneath the ice, but they're geothermally active. We can see that in the plumes that escape from their surface. So that gives rise to the possibility that there could be life on even these moons outside of the habitable zone of our own star. These other techniques like James Webb looking at planetary atmospheres, it could look at atmospheres of planets out to maybe 30 light years from Earth and investigate the possibility or the composition of those atmospheres and see if there are signs of life within them. So that's pretty interesting. But again, compared to the vast scale of our own Milky Way galaxy, which is 100,000 light years across, just investigating around 30 light years away isn't very helpful. So while these in situ methods and these remote sensing methods are very interesting, SETI as a method can really take us beyond our immediate neighborhood and encompass, the entire galaxy, which is why these other techniques of radio and optical telescopes we think are also interesting, as are these other methods. So again, when you think of the fact that there are potentially 10 to 60 billion habitable world candidates in our own galaxy, you want to do as much as you can to investigate the entire vastness of the galaxy as possible. So SETI programs at the SETI Institute involve using our own Allen Telescope array in Northern California. They also involve the Very Large Array, which is an array of 27 large 25-meter dishes that, again, like our own radio telescope, act in coordination with one another. They're a so-called interferometer. Each of the telescopes of the Very Large Array are about the size of a 10-story office building. So it's a massive array and very sensitive instrument. And we have a partnership with the National Radio Astronomy Observatory that runs that center to capture the entire field of view of whatever other phenomena that telescope might be pointing at, which is usually a point source. They might be looking at a pulsar or a variable star or some other little phenomena, but the field of view is much bigger than that. And we're now capturing all of that, sending it through fiber optic links to our own set of computers and looking for other interesting phenomena that could be signs of technology or intelligence elsewhere. And then we also have a program called Laser SETI, which is a global project where we're putting observatories. These are camera systems like you see here at different observatories around the world. And the idea is to look at all the sky all the time in all directions to look for potential laser pulses as, again, like radio signals, as a proxy for life and intelligence. And lasers also have the ability to be detectable from very, very far away. Right nearby, most of you over there in Berkeley, up at the Lawrence Livermore National Labs, is the world's most powerful laser used for energy research. And if you took the output of that laser and you bounced it off one of our big optical telescopes and sent it into space, it would outshine the sun by 10,000 times. So lasers result in another sign of technology that are interesting to look for. So those are different SETI programs at the Institute, and all of these are privately funded. There's no federal funding for these programs like there is for the other research we do. Some of the new technologies and innovations include, of course, the Kepler Space Telescope, which mission ended in 2019. The TESS mission, which launched and started collecting data in 2018 and is still going. And then we have the Curiosity rover, and now it launched in 2012, and then in 2021, the Perseverance rover established a foothold on Mars. And in 2022, we have the James Webb Space Telescope for the first time collecting data now that all of its mirrors are aligned. And we're very excited about the science that's going to be derived and the new knowledge, and then new questions that are going to be derived from that mission. And again, using the Very Large Array in New Mexico as a SETI project is brand new, starting in 2023. We're still building the hardware, the computers, and other elements of that. So we'll be doing experiments starting next year. So what kind of new knowledge has been gained in just the last 15 years? What's sort of new and exciting in this field? Well, we now know that planets are ubiquitous and they likely outnumber the stars. We know that planet formation is now generally understood, and it's a byproduct, a natural byproduct of the formation of stars themselves. The image in the background here is what's called a protoplanetary disk. It's part of the phenomena that occurs when a star is born and begins to spin up and then ignite. We know that habitable zone worlds potentially number in the tens of billions in our own galaxy. And in theory, life can exist outside the habitable zone, as we've got good reason to believe that the conditions could exist even on the icy moons of Enceladus and Europa for life. We know that Mars was once warm and wet and ocean covered, and it looked like Earth. So instead of being, the orange planet we know today, it was also once a blue world. And the study of extremophiles suggests a wide envelope for habitable environments. In other words, life exists in conditions that we previously thought were not possible. Venus, Mars, Enceladus, Europa, Titan, all of these are candidates within our own solar system, potentially for life, either past or present. And then we also know that our close neighbor, Alpha Centauri, close as in 4 light years away, has at least 3 known planets. And then life and environment co-evolve, and they are inextricably linked. So this is all, kind of new knowledge that has been built over the last 15 years of activities. Just a quick dip into this icy moon Europa and why people think that this is interesting. Well, again, as I mentioned, Europa we know is covered in ice made of water, not methane or some other weird chemical, but H2O. And its surface is several kilometers thick of ice, but we know under the ice is a liquid ocean. And we can see, as you see those sort of plumes or jets of material ejecting from the surface, that's because the core of the moon is hot. And the reason for that is the moon is subjected to intense gravitational forces because of the size of its host planet Jupiter. And so it's always getting torqued and twisted. And therefore there's a lot of heat in the core of Europa. And ultimately, that heat makes its way to the surface and causes these eruptions. And that's very interesting because on our own planet, we know that there are these deep ocean vents that are miles below the surface of the ocean. And therefore, there's no possibility that photosynthesis or the life forces that require sunlight have any impact on these environments. And yet we find thriving ecosystems of plant and animal life 7 miles below the surface. And that is what makes scientists curious about why not that same phenomena on Europa or Enceladus, where you've got heat, you've got water, you've got the building blocks or basic elements behind life. Why not life? So we'll see. And there are planned missions to Europa and ultimately we hope also Enceladus to try and answer that question. I'm just going to close with a couple of notes about our education programs. We have education programs for the Girl Scouts, where we develop STEM badges in space science and exploration. And each year, hundreds of thousands of young girls complete the exercises and activities that we put together for them and help promote STEM and sciences in young girls. And we have a program for science teachers called the Airborne Astronomy Ambassadors Program, where we take math and science teachers from underserved school districts throughout the United States, and we give them the opportunity to fly on this plane and do science and learn about the kind of science that's done on that mission and integrate their experience into their classrooms and again help promote more interest and excitement around science and STEM. And we go in, and this program's been going on for 10 years now, and we measure the impact on student learning in the sciences and science literacy, and the results are quite dramatic, which is why NASA has continued to fund this for a long time. We have a program with community colleges bringing NASA scientists and NASA-funded researchers into contact with teachers in community colleges all across the United States teaching astronomy, which in many cases may be, as an introduction to science course. For many, it's the only course beyond high school in the sciences they might take. So the idea is to make them as impactful and as exciting as possible. And that's a great program. And we have also a program every summer where we bring in undergraduate interns to work one-on-one with our scientists. So outside my door now, there are 16 brilliant young minds that come from all over the United States, actually all over the world, because some of these students are from other countries, but they come here and work with our scientists for 10 weeks in the summer and have an extraordinary experience. So education, again, and education programs is a big part of what we do. Just for some closing thoughts, there's of course the understandable question that comes up from time to time is, hey, that's all really interesting, SETI Institute, but why should we bother with this? Don't we have more important problems to solve? Well, indeed, we have some important problems to solve, but ultimately, if we don't do basic science and research, we have no chance of addressing the tough problems that face us. Fundamentally, research and exploration exercise that most human of traits, which is our curiosity, which not only unites us and drives us, but also is basically the engine for invention and discovery, insight, and understanding. So we think that basic research, regardless of the field of endeavor, is just critically important as the precursor to everything related to invention, innovation, and technology. And exploration also stretches the limits of technology, which benefits everybody. It's one thing to make instruments that work here on Earth and do make sensitive measurements. It's another thing to put them on the surface of Mars or to send technology to great distances and have it operate and be functional. So we get a lot of benefit out of that. So our work ultimately informs research in areas that include climate change, asteroid and planetary defense, communications technology and signal processing. Even cancer research is informed by some of our work about extreme biology, life forms, material science, sensor technology, and instrumentation development are all the kinds of areas that we get involved in. So ultimately, we think that without basic research, we cannot advance as a species, which is why we think the kind of work we do and others do in very basic fundamental sciences is so important. And there, by the way, is a Muamua, what we think it might have looked like if it's a rock. So ultimately, we think ours is a journey of ultimate discovery. It's about understanding our place in the universe. It's about leveraging our curiosity for the advancement of human knowledge. It's about being the archaeologists of our future. And ultimately, it's a journey to discover ourselves in the process. So are we alone in the universe? We can find out together. You can get to know what we do at the Institute. We have a website full of stories and articles and so forth. We have a YouTube channel full of videos with lectures and talks and panel discussions, all kinds of fun content on the SETI Institute YouTube channel. And again, we can find out together. And I'll send this information separately, but I've got some links here to different programs that we do in outreach and education, lectures and talks and things like that your group might be interested in. So I'll send those over to Joe separately because then they're easy to share and might be of interest to some of you. So with that, I'll end the show. I think I talked for too long, as I tend to do, but happy to entertain any other questions that you might have.
I think, Roger, you had a question on the chat. Would you like to ask that?
Sure. Yeah, you probably get asked this often, but I'm just wondering, has SETI been approached by Elon Musk or others who feel that once we finish trashing Earth that we'll have another planet to go to? And do you think that he's serious about that, and could it be successful?
Well, I think Elon is serious about wanting to go to Mars and wanting to have people on Mars. He has not come to us. I mean, we would like him to come to us and maybe, if he's serious, to ask about, well, how difficult is it? Elon has famously said that he'd like to die on Mars, but not on landing. And, one of the things we'd like to say to him is, well, the good news is that's extremely easy. It is a lethal environment. It is not a good plan B. It is not like the backup plan for where to go after we, hopefully do not, but we're on the wrong path now in terms of trashing our own environment. So, yeah, we're actually, interestingly, NASA has a whole office that they call the Office of Planetary Protection, and that is both to prevent the forward contamination of other worlds we might visit, and also to prevent the backward contamination by bringing things back to Earth that might be potentially hazardous to us. And SETI Institute has the contract for that. So for NASA, for planetary protection. And that contract involves trying to educate the public and also the commercial space industry about planetary protection and its importance. Even from a scientific point of view, while we think, we think that ultimately will be very helpful to have scientists on Mars to, study the possibility of life and investigate some of these basic questions. But at the same time, we don't want to discover ourselves in the process. We don't want to contaminate Mars with our own biology that might, then give us the wrong impression. So we think we should be very careful about, the extension of the human race into other worlds. But generally, no, we haven't been approached by Elon about his desires to go to Mars. He's going to do what he's going to do unless, there are sort of global policies, which, maybe the UN should consider now that, the technology does exist and can exist in private hands to go great distances and even to bring people great distances. I think it may be time for some regulatory oversight on those kinds of endeavors. And then, there are other endeavors which are, more about bringing billionaires into space for tourism. And, again, that's not something we're particularly interested in.
Thank you.
I think we had a question from Jyoti.
Yes, thank you. About the form of life, the human life, I mean, the life on Earth is DNA based and carbon based. Have we thought of another element based life?
Sure, that's a great question. We get that question a lot, and the answer, of course, yes. We're trying to think of that. We're always trying to ask ourselves, how do we look for life as we don't know it? it's certainly fairly straightforward to look for life as we do know it, because we kind of know what to look for. At the same time, I think there's a notion that, just as the laws of physics and chemistry are likely to be universal, at least in our known universe, it may well be that the laws of biology are similarly have common roots to them. One thing that's interesting about life on Earth is, if you're familiar with the periodic table of the elements, you'll know that the elements with just one proton, one neutron, one electron, hydrogen, for example, happens to be the most abundant element in the universe. And as you go up the scale on the periodic table, the elements go down in number. So what's interesting is you talk about some of the lower complexity elements like carbon and hydrogen and nitrogen and oxygen and helium and so on. And so what's interesting is life evolved and formed with these most basic and fundamental building blocks. So it sort of begs the question, why would life skip over the most abundant and the most sort of basic building blocks and do something more complicated? Now, it could be that life might make steps beyond carbon-based life if it had a chance to evolve into higher order elements as the building blocks. Of course, we are also building machines out of silicon and other materials. So in a way, we are an evolutionary process, potentially creating what some might consider life, or what might ultimately evolve into conscious beings out of higher order elements. But again, biological processes are likely to be based on the fundamental and most abundant building blocks. Nevertheless, bear in mind that the diversity of species on our own planet is massive. And so, even with those, with common building blocks, there's lots of different branches or paths on the tree of life that could be taken. And, if it weren't for an asteroid impact, this meeting might be taking place by a lot of creatures that look a little more like dinosaurs or reptiles. So, the pathways to where we are and who we are quite complex and narrow, and any number of other branches based on carbon could still have evolved in interesting ways. So we do think that it's likely that the building blocks are the same elsewhere, but the outcomes could be very different for sure.
Thank you.
Do I have any more questions out there? I don't see any. In that case, I'm going to ask one last one. And I believe Australian scientists earlier this year detected a very strong radio energy burst from an unknown source object way out there. There's a certain periodicness to them. Are you familiar with that, or any updates?
Yes. So there is a phenomena that is a recent discovery called fast radio bursts. And these are extremely energetic bursts of energy that we observe in the radio spectrum. So we observe them with radio telescopes. And as far as we know, they come from very far away, from deep space beyond our galaxy. They seem to come from other galaxies. And to give you an idea of how energetic they are, based on what we can observe through their impact on our instruments, we know that, for example, in just a few milliseconds of time, these objects emit more energy than our sun does in an entire year. So they're massively energetic. We don't know what they are. They are perhaps now among the most intriguing objects in astronomy. So if you're wondering, like, what are the kind of new and exciting areas in astronomy, fast radio bursts are one of them. Interestingly, there's a group in Canada called CHIME. So this is a group that was trying to map the intensity and prevalence of hydrogen in our galaxy. And so it's a project called the Canadian Hydrogen Intensity Mapping Experiment. And so they built this interesting radio telescope that, instead of looking like a dish, it looks like a big half pipe, like what the snowboarders go in. So they built these radio telescopes where it's a series of half pipes and they take up a lot of space, like the size of a football field. But instead of focusing on a point, they focus on a line. So the antenna that the dishes focus on is in a line. And so there's a series of these in parallel. And for reasons, I guess, that we don't necessarily understand, this particular kind of telescope turned out, quite by accident, to have been the most prolific instrument for discovering fast radio bursts and also repeating radio bursts. Because when they were first discovered, one of the questions that was asked was, well, do any of these repeat? And as you already observed, Joe, and have read about, some of them do repeat. But we don't know how far away they are. So one of the things that you want to do if you want to try to figure out how far something is, you want to observe it from different perspectives, different angles, so you can kind of triangulate on it. So the CHIME team decided they wanted to build what, so-called outrigger telescopes and put them in different parts of the world to investigate this further. And so they were looking for a location in America to add a second antenna or dish or bit of half pipes. So there's one in Northwest Canada, and they're building another one in the eastern part of Canada now. And the third one is actually going to be built at the SETI Institute's Hat Creek Radio Observatory up in Northern California. So we have a big bit of property up there where our own Allen telescope array is, and they've already started work on laying out the foundations for that radio telescope. At probably a couple of years to be fully built and deployed. But with that CHIME outrigger at our observatory, the feeling is that we'll be able to begin to triangulate and actually see, well, exactly how far are these fast radio bursts? Are they in our own galaxy, or are they indeed outside our galaxy? And so we'll learn more about them. But it's a great question, and it is one of the new and intriguing mysteries. And I think when James Webb really starts going into high gear, just like Hubble, it's going to make discoveries that we will think, wow, we couldn't have even imagined. So we're very excited to see what comes out of that mission.
Okay, any other questions? And if not, I want to thank you, Bill. This has really been a wonderfully engaging presentation. I can tell by the number of questions you've received from a variety of people. Also, a fairly big audience for us, well over 30s. That for us is a large audience. So it only speaks to how much interest there is in the quality of your presentation. So again, I'd like to thank you for donating several hours of your time to Ashby Village.
Well, it's a pleasure. Thank you for having me. And if any of you find your way down to Mountain View and want to drop in and see us, we're right close by, and we do have sort of an interest. We try to create a visitor experience to make it interesting for people to come and visit us. And it's always fun in the summer as well, because we have our summer interns here, which add some new energy to the place. And in a couple of weeks, we're going to be welcoming over 70 additional PhD scientists in both machine learning and AI and different science domains to work on 8-week projects, half of them for the Department of Energy, half of them for NASA, using applied AI and machine learning tools to really tackle some intractable science and technology questions. So it's going to be a fun and busy summer here for us, but love to have you visit. You can go visit the Allen Telescope Array. And of course, for any of those of you who have already become, Bitcoin billionaires, do think about us and our science needs. Or if you sell your next startup to Google, keep us in mind. But any case, it's been a great pleasure talking to all of you, meeting you, and again, Joe, if we can help with other speakers, be it from NASA or elsewhere, that you would like to bring into your program, just let me know.
Oh, I will. Thank you very much.
Okay.
Thanks
Very
so much.
welcome.
Thank you.
All right. Take care, everyone.
Ooh.